Uh, it's a very glad to have a chance to attend this meeting. So my slides is about the study of the local limited load of a nozzle with a corner crack on the combined loads. And my name is Ting. I'm from the State Key Laboratory of Nuclear Power Safety Technology and Equipment. And this slide is generated by my colleagues and me. So I was a representative to deliver these slides.
It doesn't work.
Okay, you keep on your keyboard. Yeah. Yeah, the outline covers 6 parts. The first one is background. So, as you know, the equipment failure is a common in practice applications, but if it is a core in the nuclear power plant, it will generate a disaster. And the structural integrity of the key component, such as the reactor pressure vessels, steam generators, is designed very well with the code and standards. So in the engineering practice, small cracks are often discovered during the manufacturing and operation. These cracks are more prone to propagation on the certain load transit, and the nozzle areas exhibit structural discontinuity and stress concentration, leading to the complex stress state under combined loads, make it susceptible to fatigue crack initiations. Yeah, the structure integrity assessment method based on mainly about the geometry and the material properties, defect characteristics, and the load combinations. And we often use the FAD method to make the assessment. And how to obtain accurate fracture analysis parameter is one of the foundation of the structural integrity assessment. Here gives some key method for the stress intensity factor and the J-integral methods. So the safe methods include several methods, and in the nuclear industry, the influence coefficient method is more popular. And the J-integral also, we can use the a priori and the finite element or the reference stresses. And the J-integral methods mainly for plate, and the pipe, and the a priori needs the finite element assessment analysis. Based on the limited load value, the reference stress method can be used to estimate the appropriate J-integral. So the research target is the nozzle with a corner crack, and the load combines the internal inner pressure, actual loads, and the bending moment. And the target we will make the limited load estimations and the influence coefficient method, and the reference stress method for J-integral estimations. So the mainly target for this research is to extend the application of the scope of how to make engineering engineering estimation of the corner with a nozzle with a corner crack situations. Okay, here is the model. So okay. This is the geometry of a nozzle, and it contains corner defect and the loads and the structural non-dimensionalizations and the definition of the ratio loads applied. So the FA, the finite element assessment, about 320 models covers the parameter range and then the fit one, two, three, four. Yes, five dimensional parameters. And the material is use ideal elastic plastic material, including the pressure, actual loads, bending moment, and the limit load determination is the plastic stress analysis. So this is a result of the limit load affected by the external loads of the nozzle. It shows the bending moment is have the negligible effect, and the tensile load reduce the loading capacity compared with the compressive loads. And for the limited load compared with the finite element analysis, it shows the small radius and the large thickness of a nozzle. It generates a more conservative result. And the other hand, the large radius and the small thickness of the nozzle, the result is not so conservative. This is normal. It's a common safe method for a standard rule for the nozzle corner. It's about the API 579 and ASME section 11. So the right of the slides is stress distribution of the complex loads. You can see that under the pressure, the stress is approximately linear distributions. But for the complex loads, more complex distributions, and univariate polynomial function cannot accurately characterize the stress field. So we decided to use the bivariate crack face stress fitting method, and mainly for the stress fitting on crack face. So the result is about the characterized by the variety polynomial shows close fitting with the actual stress distribution on the crack surface. With the relative error, it's mainly within 3%. Okay, this is a geometry and a mesh model. The crack tip, we use the C3D20 reduced element, and the corner crack surface angle from 0 to the pi divided 2. And the material characteristic is the ideal elastic material. And it shows by applying a unit pressure load individually to each term of the stress fitting function on the crack surface, the corresponding stress intensity factor, Kij, can be calculated, thus obtain the influence coefficient Ij for each polynomial term. To generate this coefficient table is for the further engineering estimation. It's much more convenient than make another FEA model. Yeah, this is a crack tip and SIF compare under passes. And the SIF, we make the average result between the path 3 to path 8. This is a SIF validation under the pressure and a SIF validation under loads combinations. This is under loads combination for crack front points from the angle theta from 0 to the the half of the pi, and safe validation under thermal loads. Okay, this is for the estimation J integral with the sigma reference and the load combinations. We also use about 280 validation conditions to compare with the reference strips. Yeah, this is also the model for the geometry, material property, and the loads, and the finite element analysis model, the J integral path independence. This is J integral estimation under pressure. The dimensional effects and the crack size and shape. So the result is that then divided by JE and the limited loads versus the R6 option 2. It makes a conservative result. And on the internal pressure load, the curve of the validation model are relatively concentrated, which demonstrates that the rationality of the simplified nozzle corner model use the through crack plane model. This slide shows the J integral estimation and the combine the loads. And this is an assessment example. This flowchart for determine a critical crack size using a failure assessment diagram. First, we will collect the loads and the geometry of the nozzle corner and the initial crack size by the NDT or by the some standard or rules. We will calculate the safe and calculate the lifting load, safe load ratio, crack ratio, and assessment point. So if the assessment point LR and KR satisfy the criteria, then we got the we will make the initial crack size change. So if not, we will get the limiting crack size. How to make this conjunction is about in this figure. The assessment point reach the FAC curve, it will not satisfy the pattern. Then we get to the limiting crack size. Okay, this slide shows the parameter of the assessment examples. Also, we give the dimensional in dimensional values and the materials. It's traditional. It's traditional for the RPV. It's a 16 mmD5, and we use several transient loads. And the loads are internal pressure loads, the nozzle actual force load, bending moment, and the temperature field load. Yeah, this is the result. The critical crack size under variation operation conditions. In these 4 figures, we can draw that with the point C, that is the surface point on the circular crack surface. So as the evaluation point, the critical crack size under the most hazardous scenario is determined as 23.7 millimeters based on the operation condition 1. And some conclusion and discussion. The the totally research is about the limiting loads and safe calculations and the J integral. So first, for the limiting loads, it's based on the cracked plate model, geometry simplification, and the stress equivalent, and perform for the nozzle corner structure based on the local limit load solution of through cracked plate and biaxial force and through thickness bending load. The local limit load of the nozzle model with the corner crack is estimated. And for the safe by variety stress fitting polynomial is adopted to characterize the complex stress distribution on the cracked surface on the combined loads. This is the most different research result between the traditional the one parameter fitting method. And based on the influence coefficient method, an estimation method for the stress intensity factor at the crack front of the nozzle structure with a corner crack on the combined load is derived. And for the J integral, by applying the local limit load estimation method and based on the reference stress method, the J integral value is estimated and compared with elastic plastic finite element result. And finally, based on the finite element calculation result, the local limit loads estimation formula is modified. And there is still we can do further jobs for the limiting load. The more load conditions can be considered, such as shearing force, torque, and other loads. And during the model is simplification, the reinforce effect of the nozzle was neglected. In the future, research and modification can be conducted on the estimation method under more combined loads and make it more accuracy. For the sieve, the influence coefficient is affected by the crack location and the crack shape. More parameter structural influence coefficient table to meet the needs for practical engineering applications. And for the J integral, the predicted values are over conservative for several cases and can be further corrected to obtain more accuracy J integral estimations. Yeah, that's all for my slides. Thank you.